Today we're going to repair a vintage MXR 6-band EQ. This is a vintage MXR EQ. Writing's worn off, as you can see. I think it's manufactured in New York, so it's not manufactured by Dunlop here in the Bay Area. It's broken, and the fault is described as it just doesn't work. No signal comes out. So hopefully that'll be an electrolytic cap that may have gone, or a wire come loose. It could be something fairly simple when the power supply is broken on a vintage piece of electronics like this, especially because it runs on a battery, and so there's no power supply circuit to deal with. I don't think I'm going to run it on battery. I'm going to put a connector here, and from a previous video, you know, I have this circuit that I built, or I had fabricated, and it's got a lot of filtering on it, so it cleans up the power supply really well. But it's also got a -8, it's got a +16 and a +9 volt output. So I'm going to use that +16 and see if I can give this some more headroom, and so I can have it so it's not adding its own level of distortion when it's further down the pedal chain. So I think that's going to be quite an exciting mod. So first of all, why don't we have a look at the schematic and see if there's any challenges in that schematic, such as electrolytic capacitors having values over 16 volts, or sorry, less than 16 volts, which may cause a bang or a small explosion. So here's the schematic. It's a fairly basic design. It's got 1, 2, 3, 4, 5, 6 EQs. These are bandpass filters, I would think. I'd have to trace it out, but we can do that. We have a gain stage here, and then these are the center frequencies, 100, 200, 400, 800, etc. of each one of these bands. So once it's working, we'll trace one out and just see what the frequency response is of one of these, and then the output stage just goes straight out. So it's a reasonably easy design to get your head around. The power supply, I don't quite see on this drawing. Oh, there it is. There's a power supply. It's a 9 volt battery, and what we have to look out for here are some of the electrolytic caps to see if any of those have blown, and double check that they are electrolytic caps. Like some of these larger values, like this 1 microfarad, could be an electrolytic. We have to find out through inspection. There's another what could be electrolytic, or they could be tantalums. I don't know till we take it apart, and part of the inspection is to see if there's any leakage in the capacitors, as well as just checking the integrity of the battery connection and getting power supplies to each one of these pins that I don't know what type of chip they are yet. Are they all different? LO22, LO22, and this says 1456, 1458. Well, we can check all that out when we take it apart, but if the dual op-amp packages, I would expect to see 3 8-pin ICs in here. So let's take it apart. I've unscrewed the screws. There was actually only 2 screws. We've got plenty of screws here that we can put 4 on. So when we take it apart, it's fantastically old. Now, one of the things to notice is this PC board looks like it was kind of hand done. Can you see all the traces are curves? We've got the 4 op amps there. I'll have to get my magnifying glass out to see what numbers they are. Do that in a second. And I'm not also seeing any electrolytic caps, which could be a good thing. Here's the probably higher values with the tantalums, but this looks like 100 volts, 400 volts. So I think the ability to make it a higher headroom pedal should be good. And then here's some very old looking wire, and then oh look at this. Yeah, that's not so good. That's pretty hacked. And so hopefully that is our only fault. I'll have to look and see. So we can remove it, actually. Take it out. MXR. So it says MXR, so it's not marked non-MXR or whatever. And these are the sliders, and I think these are date codes. And I'm suspecting 79, week 45 of 79. I have to double check, but right now I'm going to say 1979 week 45, and then inside, whoever assembled or tested each part got to put their little autograph or stamp in this little sticker. So quite cool. Alright, I'm gonna put a battery in now and hook it up to the SIGGEN and scope and just see what we got. Oh, there's a piece of tape here as well. I don't know what that tape was for, but now I've pulled it off. Oh dear. Well, hopefully it didn't break anything. I don't think it did. Okay, let's get the battery in and get it hooked up to some instrumentation. Okay, SIGGEN here, scope here, battery here. So let's just hook it on. Some signal there. Oh, no signal there. Press. Yeah, this is intermittent. So hopefully that's the only problem. That this beat up old connector is and the solder joints on it are awful. Is what our issue is. That would be fantastic. So half of me doesn't want to drill some holes in this vintage box, but seeing all the writing scratched, I think I'm fine. Okay, alright, let's not make this battery operated anymore. Let's get some holes drilled in this thing, get the power supply wired in, then do some frequency response tests. I've got it all wired up, so here's the voltage booster. So this is giving me a 9-volt supply and a 16-volt supply, and this is all surface mount that I had made, and in contrast to the old-fashioned circuit board there. So I've got it hooked up, SIGGEN coming in. I've got a 400 Hz signal coming in, and that's what we're looking at on the oscilloscope screen, and I've set the 400 gain to max currently on the 16-volt supply. So if we take it back down to 9, you can see we're clipped. So we're getting a much improved headroom with the 16-volt supply. I actually ran the 16-volt supply for about 8 hours just to check that I wasn't going to break any of those tantalums that was in there, and everything looks fine. So that's our 400, and so if we bring it down, that's 400 fully attenuated, that's the middle, and then that's 400. So let's do the frequency response. So that would be 300, 200, and you can see it gets smaller, so it is a bandpass. And then back on 400 and go up to 500, 600. Yeah, it's a bandpass filter. I'll probably trace it out later. I've set the signal generator now to 800 Hz. Use the 800 slider, so it goes 100, 200, 400, 800, and I have to check online what these are, if that's 1600, and this one would be 3.2. I'm pretty sure there are. So let's just do the 800. That's full gain, and then that is back on 9 volts. So you can see we've got terrific headroom in this pedal now. And let's do a manual frequency sweep. So let's go down in frequency. Yeah, it's a bandpass. And as I go higher, so that's at 1.2 kilohertz, and then back down to 800. Cool. This feels really good. We're going to do a number of frequency response measurements now. So I've got everything in the attenuated position, and what I'll do is, as we do each one, I'll turn them up. So first of all, let's do a reference with everything down. Now we have the reference measurement. Let's turn up 100 Hz, do the measurement again. Won't go all the way to the top because I know it clips at the top. And now I'm going to repeat it with all the other ones, and let's take a look at the results. So here's our frequency response curve, or set of curves. The 100 is a low pass filter, 200 bandpass, 400 bandpass, 800 looks weird. It's kind of got this flat top and it doesn't have as much amplitude. 1.6 is fine, and then the 3.2 has this weird frequency ripple on it. I don't know what, like a lot of harmonic content, so that That's weird. We'll always have that one down pretty low though, so those components should be attenuated, because I just don't want a lot of fizz coming through the pedal. The most interesting thing to me right now is to try and understand why the 800 slider or the 800 hertz filter looks like that. So I took the pedal apart, checked all the values, flipped the board over, and it was full of sticky goo on the surface of the board. Could be flux. It was on the side where the pots, the sliders, are exposed. Let me show you. So it was on this side of the board. Maybe something was spilt on this and it's just stuck there as a goo, and that goo was conductive. Once I cleaned the goo off, the 800 performs really well now. In fact, they all do, and even that high frequency ripple has gone away to a certain extent. That high frequency harmonic ripple has gone away. Let's look at the results, and you can see here quite clearly. I did the measurement 3 times with the pot on different values. So this is like a max val. This is about at 2/3, and this is lower down, and it looks good. We've eliminated high frequency, so this is our reference here at the bottom, and then here are all the different bands, and it works. It really works well. So quite pleased that I decided to do a frequency response measurement and find out that one of the bands was indeed at fault. I checked all the values. I didn't really want to take it apart and start swapping caps out because the board's so old and didn't want to ruin it, but once I cleaned the goo off, the pollutant, the conductive pollutant, it all worked fine. Let's do some tone tests now. I've got a Strat plugged in now, pedal off, and it's on the clean channel of an Orange Super Crush 100. And we've got the tone shape in here, and we've got it set to high voltage, and so I'll plug this guy in now. And remember, this has a 24 volt power supply, so it puts out a big signal. So we're overdriving the front of the amp. But this isn't contributing to that distortion. It's passing straight through, apart from the fact that we've got this tone shaping going on here. So it's not contributing as a boost or as a distortion, or mainly a boost, but it is a pure tone shaper, which is neat, which means I've got more control over my signal. I have the Les Paul hooked up now. This looks like a microamp, but there's a video on the link up here at the top, but this is modified into a Distortion Plus. Actually, it can be both a Distortion Plus or a microamp by flicking these switches. And then here is our EQ, so nothing's engaged. So that is a JCM800. So let's bang on this guy. So that's quite a lot more distortion, which is good for this kind of pedal setup. And so let's add some mids. 800, 400, just tick it up a bit. Let's take some of the high fizz out as well. Let's try it like that. That E sounds pretty neat. A sounds good too. It's like the 80's all over again. It's quite a neat sound. It's in 9 volt mode, so if I switch it up here, I don't think it'll make any difference though with this setup, because we're using heavily clipped stuff. However, I do think it's a little clearer, because thinking about the theory, this will clip more when we have more gain set here with the 9 volts versus the 16 volts. So it feels a little cleaner. Well, clean relatively. I don't know if I just want to hear that difference. The 16 volts just feels a little tighter. It's a feeling that I've not analytically proven. This is set to an actual microamp. Switches are in the up position. Still got quite a bit of gain going on here in the mids. And it's 9 volts. So let's put it on 16. I think it's a little crisper with the 60 volt. Obviously it's going to have much higher headroom, and it's just how do you quantify that by plugging in a guitar and just trying to perceive there's a headroom improvement when the amplifier is probably also clipping and leveling things out as well. Anyhow, that's our video. I got the pedal from Blackstone Musical Instruments in Lancashire, England, from a good man called Chris, and hopefully I'll be able to get back there again when I go visit England again and maybe get another vintage pedal from him. Thanks a lot. Please like and subscribe.